We did a little bit about remote sensing for cyclones, and this is a brand new paper that just came out in AGU's EOS journal. It's like a newsletter, but it has articles by these people here, and it's called Chasing Cyclones from Space. We have looked at visible infrared, we looked at trim precipitation radar, trim microwave imager, special sensor microwave imager, and so on, to look at various aspects of the cyclone, the core dynamics, and cloud bands, rainfall, etc., etc. This is the pioneering use of satellite-based synthetic aperture radar to characterize tropical cyclones in near real time, which has provided crucial new tool with which to forecast powerful storms. Anything that can improve the process understanding and provide data for assimilation into the forecast models to improve forecasts is obviously going to be very useful. Synthetic aperture radar is basically a radar. Radio detection and ranging is active, so it sends radio pulses and then measures returned signal with an antenna that amplifies it. Basically, if you measure the phase and the amplitude, you can create a synthetic aperture effect to create two-dimensional images which provide incredible details at high resolutions of the order of 100 meters, for example, in a swath that is about 500 kilometers, I think. And there are, of course, issues. Right now, the ones that are being used, like Sentinel-1 and RadarSat-2, are polar orbiting. They are not geosynchronous, so they are opportunity looks at cyclones. Plus, they collect a lot of data, so the data is often dumped to save space, so you have to plan for data gathering when you are chasing a particular cyclone. So with all those caveats, let's start. The blurb says synthetic aperture radar provides highly detailed views of wind speed at the ocean surface under tropical cyclones as they travel and evolve, right? This is astronauts aboard the International Space Station providing the close-up view of the eye of Category 5 Typhoon Maysak in March 2015. Last year marked the first time that tropical cyclone wind data derived from SAR scans were incorporated into forecast products in near real time. So this is 2021 referring to 2020 experiments of using SAR wind data to improve to make cyclone forecasts. Another blurb says SAR's unique ability to record the roughness of the ocean surface directly allows for the creation of high-resolution 2D maps that significantly improve estimates of a storm's eye location. So you can see the images here. This is Himawari 8, the Japanese SAR satellite, and RadarSat-2. There is the scale for reference. These two satellite images of Super Typhoon Goni over the Pacific Ocean were taken at almost the same time on 30th October 2020, when the storm was close to peak intensity with wind speeds exceeding 155 knots. I think that amounts to probably almost 300 kilometers per hour, but please check. The visible light image the visible light image from Japan's Himawari 8 satellite left at 500 meter resolution captures the reflection of sunlight from cloud tops and shows transverse bands in the cirrus clouds. So you can see these bands. A sloping eye wall, clearly see the stadium shape that we talked about before. Spiral banding features circling more than 360 degrees, so some of them you can see making more than one circle here. And a clear eye, indicative of an intense tropical cyclone. The wide swath SAR image acquired by RadarSat-2 satellite here with 100 meter resolution shows a radar backscatter return from ocean surface and patterns from convection cells. Rain bands and outflow boundaries along with spiral wind streaks are seen here. So you can see this incredible amount of details of the meso vortices and the eye wall and the sloping of the eye, the bands, the spiraling in bands, and so on and so forth. Here is more detailed data. So this is showing wind speeds here going from 0 to more than 80 knots, almost I think almost 100 knots here. This SAR derived wind speed map here shows the I region of Typhoon Haishen on 5th September 2020 at 21:17 UTC based on radar data from RadarSat-2. Two-dimensional wind speed maps like this produce very accurate estimates of eye location and extent, and so location and extent of the eye, and clearly resolve steep wind speed gradients shown by strong variations in the color scale. Okay, so this is incredibly high resolution wind data that's not possible even with a recon aircraft with this kind of complete spatial structure. And the extent of winds at the critical speed thresholds that forecasters use to characterize a storm as a tropical depression, tropical storm, or hurricane. Gray dots represent SAR-derived wind speeds at each 3 by 3 kilometer pixels. So you can see here the data. In the northeastern quadrant of the map at the left, and solid black curve represents the average wind speeds at each distance from the storm center in nautical miles. So here's the distance in nautical miles, and these are wind speeds in knots. We use different units, we have to get used to them. Two peaks in the wind speed profile near 15 and 36 nautical miles from the center indicate that Haishen had a double eye wall. So you can see these two eye walls here at 15 and 36 nautical miles from the eye wall. So there is the minimum wind speed in the eye wall, there is the first eye wall, there is the second eye wall, and then you have these wind bands going out. And you remember the radius of the 34 knot giving us the intensity and so on. So remarkably useful data that can be used to characterize the storm as well as use them to forecast the cyclone. So here, this output graphic from Joint Typhoon Warning Center's automated tropical cyclone forecasting system contains information for 30th August 2020 on Typhoon Maizak's position. Past and forecast are combined here, so verification and forecast, speed and direction of travel, and the predicted areas covered by 34, 50 and 64 knot winds in each quadrant of the storm. Irregular circle-like outlines, so you can see these outlines here within the larger circles. The dashed red line and the enhanced the enclosed shaded area highlight the 34 knot wind danger area. That's what is used by mariners. ADCF system produces similar reports for every 6 hours during the lifetime of a storm. Like the 2015 tropical storm in the photo at the beginning of the article, this 2020 storm is also named Maizak. Okay, so again, you get the idea that the Joint Typhoon Warning Center is really exploiting these. There are collaborations with the Naval Research Lab, JWTC, European Space Agency, I think, and IFREMER, the French Institute for Exploitation of the Sea, which is the English translation. Here are other examples. Ocean surface wind maps, color scales showing speed in knots from a selection of tropical cyclones of various sizes and intensities from the 2020 season. Categories represent intensities at the onset of, at the times of SAR observations. You know, SAR is flying over, and whenever it gets a glimpse, has a repeat cycle of maybe I don't know how many days. The colors highlight azimuthal variations in wind speed and differences in eye shapes. You can see the differences here. And these are different, the the typhoons captured: Typhoon Bavi, Hurricane Marie, Delta, Sally, and so on and so forth. So nice collage of images. By the way, some of the Japanese people also know that this kind of circle of enlightenment is also called Enzo in Japan, and there is a joke about Enso and Enzo. Each Enso looks different, but here we can say each cyclone also looks different. The Zen Circle of Enlightenment artists also make these kind of different renditions of the Enzo. Finally, these pie charts provide an overview of SAR-based tropical cyclone collection acquired since 2015 that are available in the Cyclops archive. From top to bottom, charts show the percentage of SAR acquisitions available for each tropical cyclone category according to the Saffir-Simpson scale. So you can see the categories here and the pie chart of the percentages of SAR captured storms, percentage of SAR acquisitions available for each ocean basin here, and percentage of acquisitions available from Sentinel-1A, 1B, and RadarSat-2. So Sentinel-1A is picking a lot, RadarSat is here, and Sentinel-1B. So Sentinel is a 2-satellite constellation that has this polar orbiting configuration. Okay, so this gives us a good sense of where remote sensing is headed and how it's going to make understanding the cyclones better and details, as well as improving the cyclone forecasts. So good news, of course.